Okay, folks, section 3.2 from the text is called product and quotient rules. All right, so two new derivative rules for functions that are themselves created or combined, a combination of other functions that are either being multiplied by one another or being divided by one another, so product and quotient, okay? In the book, I noticed, first of all, let me mention, on page 187, page 187, there's a nice little table. This is at the end of the section. It's written there. End of section 3.2. A nice little table with all of our derivative rules so far, including these two rules, which are about to get covered in this section. Okay? So just as a note to yourself, you probably want to reference that table. Perhaps jot down a table like that in your notes or something like that. Be familiar with those. Okay? So all of the rules are going to be posted there, up to and including these. And they use the prime notation for the product and quotient rule in the table. Okay, kind of a nice, concise way of using the prime notation right there. Earlier in the section, when they first introduced these rules, they used the D notation, okay, which I was favoring in the previous couple of videos. For these two rules, I'm going to do it with the prime notation. I'll definitely do it with the prime notation, maybe throw some D notation up there. I'm probably going to do it a little bit differently than the way they're going to show it in the book, okay? Meaning that the order that I write the different pieces might be a little bit different. So I'll try to address that when we come to it. However, the way I'm going to do it is fine. So just because it doesn't match the book, it still works. It's the same exact expression. There's a method to my madness. This is the reason why I do it this way, okay? And I start with the quotient rule. So typically people learn multiplication before division, and then most math books introduce ideas sort of in that order, right? The multiplication rule, then the division rule. I'm going to start with the quotient rule, though. The reason is the quotient rule is a little bit more complicated. There's a minus sign, meaning instead of a plus, which we have over here. So that means that where things live, the order matters, right? If we reverse the order we're subtracting, we run into trouble. Over here, if we reverse the order, no big deal. So I like to remember the more difficult one first, and then sort of edit that into the other one. So sort of a 2-for-1. Okay. So let me first just write out the quotient rule, and then sort of talk my way through what I'm writing. Okay. So let's say I've got a function like this. Let's say I'm going to call it q of x. All right, for a quotient. It might be called f, though. You might have something else, but I'm trying to avoid f and g, because if I've got q of x is built as a quotient, meaning I've got something like that. So I'll come back to product, but let me just emphasize that we're doing the quotient rule here. Let's say I've got a function that looks like that. Okay, what's an example? An example might be something like this. Let's say I've got x squared plus 1 over x cubed minus 5x. All right, so let's say I've got a function that looks like that. All right, so that's my original function. What a lot of folks want to do is sort of just take the derivative of the top and then just take the derivative of the bottom and then just form a new fraction out of those two pieces and say we're done, okay? It doesn't work like that. It did work like that with the plus and minus, right? Our sum and difference rules was like just take the derivatives of the pieces and add them or subtract them together. But with multiplication and here with these quotients or with this division that's happening right here, it does not work like that, okay? So let me first start emphasizing q prime of x is not simply equal to f prime over g prime, okay? So it's not just the derivative of the top over the derivative of the bottom. It's more complicated than that. Okay, so if that's not what it is, then what is it equal to? So what it is equal to is, so first I'm going to write it out all as functions of x. Then I'll sum it up without drawing the of x's because they can make this take up more space. But what it is it's the bottom function, so g of x, times the derivative of the top function, so times f prime of x. All right, so you get a product up in that numerator minus, all right, minus a product of the other sort of combination. So it's the bottom times the derivative of the top minus the original top, f of x, times the derivative of the bottom, g prime of x. And then that's all over g of x, whatever my original denominator is, but squared. So we square the original denominator, which looks like this, g of x squared. Alrighty. So take that down, jot that down using this notation. There you go. All right. So while you're jotting that down or looking at that, a couple things I emphasized early on is when you're subtracting two things. So I've got this product here minus this product. the order that you write these matters, right? So if you wrote this product up front, then you're going to get the wrong answer by subtracting in the opposite direction. So the order up there matters. The way you might see this in the book is, notice here I have the F before I have the G, right? And that's the alphabetical order. And that's usually kind of conventional for math stuff, is to write list things in alphabetical order, just for kind of consistency or convenience, right? So what you might see oftentimes is this product reversed, right? The combination we need though, right? So we still need f prime of x multiplied by, so it's still the product of the original bottom times the derivative of the original top, right? So that product lives like there. But if you see it in the book written like this and you're wondering why I put the g, it doesn't matter because the order that I multiply two numbers does not matter. And the function value here, or the function and this thing, they're just numbers or terms. So I can reverse that order of multiplication, okay? So, not really a big deal. However, I like to put the g first. And I'll show you why. I have a little silly reason why I like to do this, but it's how I first remembered it when I was younger, when I first got introduced to this rule. Since then, since becoming a teacher, I've showed it to students, and I know that it's hit home with some of them because they draw my little silly mnemonic device on tests on paper, and I'm like, okay, that's stuck with them. It's good. So I made this example. We can come back to an example here. But let me just sum up this rule quickly. Q prime, right? I've emphasized in some earlier videos, the name of this function is f. And then writing f of x is great because that tells us it's a function of x. But here I could say q is equal to f over g, right? And as long as we all kind of agree that we're dealing with a function of x or a function of whatever, then this kind of makes sense. This kind of means the same thing as that, right? So what I'm going to do is just write a little bit more concise version of the quotient rule without all these of x's. Right, so we're just going to take it for granted that all these functions are of x. Let's just write it out a little bit nicer. So if q of x is this, I'm calling my top f, calling my bottom g, then the derivative of that function is the bottom times the derivative of the top, so g times f prime minus f times g prime all over the original bottom squared. All right. So that's my more sort of concise version. So look at this one, look at that one. They really say the same thing. I've just removed all the of x's, right? So if you were in a real-time class and you were bringing like a note card or something like that, that's the one I would jot down on my note card because it's a little bit more concise, right? It takes up a little bit more space, still captures what's going on. So let me emphasize we've got q of x is a quotient of two different functions, and this is my derivative. All right, so now to include my little mnemonic device, I'm going to rewrite it down here, give myself a little bit more room. Q prime is the bottom, g f prime. The more we write it, the better practice. G f prime minus f g prime all over g squared. Okay, so the reason I wrote it like this originally is because it's hard, like I said, the minus sign is important. So I know what I've got here is one of the functions times the derivative of the other, right? We see that happening. F times the derivative of g, g times the derivative of f. So I know I've got to take one original function and multiply by the derivative of the other. But how do I know which product belongs up front and which product belongs back here in this subtraction? Because the order does matter. And so I wrote it like this originally when I was younger. And then I sort of visualized this triangle, something like that kind of happening right there. Do this little triangle around that. And the way I kind of remember this is the g's live on all the corners of the triangle. So in other words, the first g lives right there. So I got a g in the corner, sort of a g in the corner, and then a g on the corner. Okay, and then the f's kind of live in the inside. Then, to determine where the primes go in this numerator, the way I interpreted this was this g sort of has nothing on it. This g has no sort of exponent or no character written up there. This g has a prime, which is not the number 1, but it kind of looks like a number 1. And then here I have a 2, which is an exponent to number 2. And so I thought like nothing, 1 thing, 2 things. Right? So I'm sort of like counting up, like nothing, 1, 2, as the little sort of augmentations on my g. And then from there I just said, well, if this g is the original function, then it must need the f prime, right? And if this g has the prime, it must need the original f. So once I plant my g's where they belong, the f's sort of come along with the ride. I remember the quotient rule gets the minus sign, and there we go. So I'll work an example in a second, but that's the general rule, okay? So I kind of visualize this triangle, and then I've had some success sort of also phrasing it this way. If you kind of erase the corners of that triangle and sort of attach it like there. It's kind of like Superman's like chest emblem, right? He kind of has that S written in there. So I don't know why. I just thought of that one time, like Superman's symbol. Kind of remember that. The G's go in the corner. Fill in the primes where they belong with the F's and the G's and everything. And there you go. There's your quotient rule. So if you like the way it looks in the book, or you've learned it before and you like the F prime G in that order, you know, I'm not saying you have to remember it my way. But if this is helpful at all, there we go. Okay. Great. So we've got the product rule. Let me now sort of convert this into our product. I'm sorry. We have the quotient rule, sort of the quotient. Now let's convert this into the product rule. If we have the product of two functions, and see how we can sort of morph the rule. So rather than call it q of x, let's say I've got a function p of x, right? And I'm just calling it that because it's the product. And let's say it's a product of two other pieces, f of x times g of x. All right, so something like that. So now I'm going to call my derivative, instead of q prime, call it p prime, since my original function is called p. So let me erase my little Superman symbol. Okay, once you've got the quotient rule memorized, so I'll emphasize, memorize that one. Now, what's the product rule? There's no denominator, and instead of a minus sign, there's a plus sign, and that's it. Okay, so if you've already memorized the quotient rule, just do those two little quick steps and you've got the product rule. I like to say as sort of a freebie, right? In other words, I'm not really remembering this as a separate rule. I already know the quotient rule, and now I just made those little modifications, and we have this, okay? Again, to emphasize now, this one has some different freedoms. So I could also write this as f prime g, right? So switch the order of this multiplication, same way we could have done with the quotient. So you might see it like that in a book, right? And now, the order that I add two things, add these products, does not matter in the same way that it did when I subtracted them. And so that gives you a little bit more freedom for the product rule. So you might also see it like this. You might see regular f g prime plus f prime times regular g, right? So don't think that the way I'm writing it up here, I'm teaching you a different formula than I think this is what they write in the book. And in the book, they use denotation. So they add f times the derivative with respect to x of g, and I think they have all the of x's in here. So f of x times the derivative with respect to x of g plus the derivative with respect to x of f times the original g, right? So to me, I don't love the denotation here. It just looks a little more complicated, but it's fine, right? So that's what you might see in the book. If you translate this into prime notation, you've got this line. If you start rearranging it, you can get back to where I came from. So all of these really say the same thing, okay? So don't feel like you have to emphasize my way. The reason why I do it this way is because this follows from the quotient rule, where everything, the order does matter. So anyway, that's the way it goes. All right. Notice that, just as I said before, the derivative of a product is not simply just the product of the derivatives. All right. So let me put the not equal to right there, just to emphasize that's not the way it works. You've got to use this more complicated rule. All right. They're not really so bad though. A lot of times with polynomial terms, we can avoid the product rule altogether. So that was sort of addressed in the homework. So I'll stop this video, pick up a second one with a couple of examples of both of these rules, and there we go. Okay.